Hi, in this video we are going to talk about the third shortest path algorithm, the so-called DAG shortest path method. We have been discussing Dijkstra's algorithm. It is very fast, so the time complexity is ordo E plus V times log V, where the V denotes the number of vertices and the E denotes the number of edges in the given graph. But on the other hand, it is not so robust algorithm, which means that it is not able to handle negative edge weights. Bellman-Ford algorithm is capable of handling negative edge weights, so edge weights smaller than 0, but on the other hand, this algorithm is not as fast as Dijkstra's algorithm. And we can come to the conclusion after all that if the graph we are considering is a directed acyclic graph, so the graph has directed edges and it doesn't have any cycles, then we can use the DAG topological ordering shortest path method, which is going to yield approximately linear time complexity as far as the number of edges and the number of vertices are concerned. So we have the vertex class. Basically, it is approximately the same as we have discussed for Bellman-Ford algorithm and for Dijkstra's algorithm. We have the name, we have the predecessor, so the previous vertex. We have a Boolean flag to be able to track whether we have visited this given vertex or not. We have the adjacencies list, it is a list of edges. And we have a distance, we initialize it to be the maximum value. And of course the aim is that we are looking for the shortest path. So we have the constructor as usual with the string name. We instantiate the adjacencies list in order to avoid null pointer exception. And we have the getters and the setters method, as well as the toString method. What about the edge? Edge is the same. We have an edge weight, we have a start vertex and a target vertex, we have a constructor with the weight and the two vertices accordingly, and we have the getters and the setters for all of these parameters. We have to use the topological sort, so I have implemented it as we have seen in the depth-first search section. Basically, a topological sort relies heavily on depth-first search. And depth-first search uses a stack in the background, so we instantiate the stack and we iterate through all the vertices in the case that it is not a strongly connected component. So we iterate through all the vertices because maybe we are considering a graph that has several distinct components, and we make the depth-first search. And basically the depth-first search is going to be implemented in a recursive manner, and we are going to push the vertices we have finished to the stack. Okay, just to be clear, in this case the stack is not for implementing the depth-first search algorithm, it is for the topological ordering. Because we are going to push it to the stack, we just have to reverse the items in the stack, and basically it's going to yield the topological order of the graph's vertices. And in the acyclic shortest path, basically we have the vertex list, we have the source vertex and the target vertex. We set the source vertex to be equal to 0 as usual, and we have to make the topological sort at the beginning on the vertex list. We are going to return a stack of vertices with this get topological order as we have seen. And basically we iterate through all the vertices, and these vertices are in topological order, so we iterate through these vertices and consider all the edges to be able to relax all of them. So it is the usual algorithm as we have seen for Dijkstra's algorithm and for Bellman-Ford algorithm. We have the start vertex because we iterate through all the edges. So we are able to call the edge.getStartVertex. We denote it as U because usually it is denoted by U. We have the V, which is the target vertex. We calculate that whether the new distance, which is the start vertex, get distance. What does it mean? It means that what's the distance from the start vertex or the source vertex? It's going to be returned by this, plus, because we consider all the neighbors of the start vertex, that's why we have to add the edge.getWeight to be consistent. And if this new distance is smaller than the v.getDistance, which means that there's a better solution, there's a shorter path, we have to update the distance to the new distance, and we have to set the predecessor to be u. Okay, And basically, if the target vertex distance has been updated so it is not double that max value, which is the initial value because we have initialized it to be the maximum value. So if this target vertex.get distance is equal to the max value, we know that there is no shortest path to the target vertex. And anyways, there's a shortest path with the target vertex get distance. So the algorithm was able to find a given solution. The show shortest path algorithms basically have a list of vertices. We start at the actual one, we add it to the actual vertex list, and while the predecessor is not null, we start at the target vertex and keep getting the predecessor until we bump into the situation when the predecessor is null. We add it to the list and we have to reverse it, and we just print it out. So basically this is how we track the shortest path itself, as we have seen for Dijkstra's algorithm and for Bellman-Ford algorithm. So let's suppose the fact that we have an acyclic graph. Basically, I have constructed an acyclic graph. In this situation, we have some edges from A to B, another edge from A to C, and a third edge from B to C. This is the typical case we have been considering for Dijkstra and for Bellman-Ford algorithm. It is a directed acyclic graph, so we are able to run the DAG shortest path method. Why is it good? Because this is the fastest algorithm in the sense that it is faster than Bellman-Ford and it is faster than Dijkstra. Of course, it is not robust because we are not able to use it for negative edge weights, and we are not able to use it when there's a cycle in the graph. Okay, we have a shortest path with value 1 going directly from A to C. What about the fact when there's a huge cost added from go to A to C path? Then we have to take some other road and have to go from A to B and then from B to C, and the path is going to cost 2 units. So basically that's all about the DAG shortest path algorithm. And why is it important? Because we have been talking about graphs. And you may pose the question that, okay, why are we talking about graphs? And basically it is very, very important because several problems out there can be reduced to a graph algorithm problem. For example, when we are dealing with web crawling, Google search, the so-called knapsack problem. For example, the knapsack problem can be reduced to a directed acyclic graph, and that's why solving the knapsack problem can be reduced to a directed acyclic graph shortest path algorithm. And basically it has linear time complexity, so it is very, very easy to solve this problem with the help of this topological sort, and then we have to find the shortest path as we have seen. And if you are interested, for example, that how you are able to construct a football team when you have some players with all the constraints, that how much does it cost to buy a player, what are the parameters of the players, for example, the speed of the player, the mass of the player, or what's the probability that given player is going to score on a given match. And basically you can find out that how to construct a football team out of these players in order to maximize your profit, which means that you want to construct a team that's going to win all the matches with the highest probability. Of course, you have to consider that you have some amount of money, and of course you are not able to spend more than the amount of money you have, and you would like to optimize that you want to buy the best player possible. And okay, basically this problem is kind of a knapsack problem, but here in this situation we have some constraints, and this problem can be reduced to a directed acyclic graph shortest path problem. So I think that these algorithms may seem to be useless, but on the other hand, these algorithms are very, very useful. Okay, not in software engineering. If you are a software engineer, for example, at a multinational company where you have to develop smartphone applications or enterprise applications, then okay, you are not going to bump into these situations. But there are several cases when you have to use these kinds of algorithms, or for example, a library relies heavily on these kinds of algorithms, and I think that it is good to know about that what's happening approximately in the lowest level. Thanks for watching.